So now we're going to jump into how inverse functions relate to sine and cosine and tangent, all the periodic trigonometric functions we've been studying. So before we get into this, I would recommend you pause the video and actually try to do this on your own, and then check your answers by watching the video. So our question is y equals sine of x a one-to-one function? It most certainly is not, because the horizontal line here crosses 1, 2, 3, 4, 5, infinity number of times. This is a definite and resounding no, it is not. So we need to find an inverse sine function. So we want to make sure we only have one horizontal crossing. That's going to require us to restrict the domain. So we're going to find a restricted domain, much like we did previously. Our restricted domain, I didn't write it down earlier, so let's write it down, is 0 to infinity. For that one, that was our purple branch over here. So what is our restricted domain for the sine function? Well, we need to make sure that it takes over the full values of the range, so from -1 to +1, but it still has to be 1-to-1. So basically number 1 says big enough and 2 says small enough, and then number 3 is kind of an arbitrary decision, but we decide it would be nice if the domain was centered around 0. So if we're centering it around 0 and we go until we get to a maximum, and then we also go the other direction to get to a minimum, then this guy right here fits the two requirements, 1 and 2, and then the third thing was the nice to have, and we were able to do that. So our new domain, as we can see, hits the minimum. We hit the minimum here at -pi/2, -1. We hit the maximum here at +pi/2, +1. So the domain restriction is going to be domain equals the -pi/2 to pi/2 interval, including the endpoints. So let's see how it looks to graph this thing. So remember that each one of these endpoints is going to swap their x's and their y's. So for the inverse, the x and the y are going to swap places. So instead of pi/2, 1, we have 1, pi/2. And instead of -pi/2, -1, we have -1, pi/2. Instead of 0, 0, we have, oh wait, it's still 0, 0. So those 3 points we know for sure. And then we're going to switch some other points as well. Like, for example, on the original function we had, I don't know, we had pi/6, 1/2, right? The sine of pi/6 is 1/2. So that's going to also swap places. So we're going to now have 1/2, pi/6. So we're going to go to 1/2 and then pi/6, right? Pi/6 is not very high up compared to pi/4 and pi/3. Those aren't very well spaced, so I hope you get the idea. But anyway, it's down there somewhere. It's closer to the horizontal axis. So as we curve from here, we're going to go up like that. And as we curve from here, we're going to go down like that. Notice that on the original function, when we reached these endpoints, we kind of leveled off horizontally, right? If we imagined this is the top of something and this is the bottom of something. Now we end with those same endpoints switched around. It's now the far right of something and this is the far left of something. So everything with inverses swaps. The domain and the range, the x and the y, the vertical asymptotes become horizontal asymptotes, blah, 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 blah. So everything gets switched. This is a new function. We call this the arcsine function or the inverse sine function, and we can use either one of these notations. Sine raised to the -1 is what it looks like, but we would say inverse sine function. That's this guy right here. And then the other one is the arcsine function. They mean exactly the same thing. So either way, you can write it either way. I tend to use the first notation just because it's a little bit faster to write, but they are interchangeable. So we restricted the domain of sine of x to the x value is -pi/2 to +pi/2. That is still part of our problem, right? We still see a -pi/2 and a +pi/2, but they are now on the y-axis. So now we're talking about that being the range of the inverse function. Okay, and then the range of the original function, y equals sine of x, is -1 to +1. Even with our domain restriction, we're still going from a -1 to a +1 for the range of our original function. So we'll put -1 to +1 in there. But now that's the left and the right endpoints right here. Those are our new domains. So domain and range switch on your inverse because you're just swapping your x's and your y's. So now we have to use that new function, the inverse sine function, to evaluate each one of these things. So let's see. This is the same thing is almost the same thing as asking the question, the sine of some mystery value equals 1/2. Right? Just like if we scroll back up a bit, we would say that what this means is the value, this mystery value that when you square it, you get 9. Okay? This is this mystery value that when you sine it, you get 1/2. And we know from the unit circle that there are lots and lots and lots of solutions here, right? For example, if we start at 0, the first place we get to a y value of 1/2 is when we get over to here, which is at pi/6. But we also know that as we rotate around, we end up over here at the same y value, but a different input value of 5pi/6. The sine of 5pi/6 is also 1/2. And then we keep on going, we get -1/2 down here, so we don't do that again. But we do hit the 1pi/6 again later on at, I guess it would be 13pi/6. Right? Coterminal to 1pi/6. And we also have, etc., bigger and bigger values and also smaller and smaller values. This is exactly because of the periodicity here, right? When we look at each one of these points on the purple horizontal line, each one of those x values is another solution to the equation. That's why we have an infinite number of these guys. But wait. We don't want an infinite number of answers because we have a function, the sine inverse of 1/2. So we have to find whichever value works with this infinite list, but it also has to be between -pi/2 and +pi/2 because that's our restricted range. It was our original restricted domain. So we have to find the right angle that's in that interval. And the only one that fits that interval is pi/6. Pi/6. There are two reasons why this is the answer. Reason number 1, because the sine of pi/6 is equal to 1/2. That's a check. Yes, we know now that that's one requirement for this to be the right answer. The other requirement is that my answer has to be between -pi/2, so that's less than or possibly equal to my answer, which is pi/6, which is less than +pi/2. Yes, pi/6 is in between -pi/2 and +pi/2, so that's a second check. And because it passes both of those tests, we know that this is the right answer. All right, I'm not going to go through each one of these as painfully slowly. We'll see that this has to be -pi/4, because it fits the same two requirements as we saw before. And this is going to be -pi/2. So be careful here. Let's make sure we write not 7pi/4, even though the sine of 7pi/4 is the right value, but 7pi/4 is not in our interval for our range. We can't get 7pi/4 as an output. Likewise over here, don't put not 3pi/2. Yes, the sine of 3pi/2 does equal -1, but it doesn't fit that second requirement, namely that it's in the proper range. Now, when we look at this one, we're saying, this is a little mysterious. We're saying that there's some value x that when we take the sine of it, we get an answer of 2. And we all know the answer to that. That one's easy, right? What x value causes my y value to equal 2? And the answer, of course, is none, because we never go above 1 on this graph. So this would just be x does not exist. You could say undefined. You could say no answer. I don't care. Just don't put a number here. All right.